Hi, good morning. Today we are going to start the next session of advanced functional analysis. Here also we are continuing our discussion on Fredholm theory of compact operators. Just to recall our propositions 5.2.7, and this says that delta lambda equal to x implies kernel t lambda equal to 0. Equivalently, kernel t lambda not equal to 0 implies delta lambda is not equal to x. Delta lambda is image of t lambda. That is, this means t lambda is onto implies t lambda is 1 to 1. Similarly, we get delta star lambda conjugate equal to x star implies kernel t star lambda conjugate equal to 0. So moving to proposition 5.2.8, this says that delta lambda complement or perp equal to kernel of t star lambda conjugate, as delta lambda is a closed subspace, by proposition 5.2.5, delta lambda not equal to x implies kernel t star lambda conjugate not equal to 0. Moreover, we get delta lambda equal to kernel t star lambda conjugate lower per. Kernel t lambda equal to delta star lambda conjugate perp. Okay. Also we have lower perp. Also we have kernel t lambda perp equal to delta star lambda conjugate. Okay. So you have to remember each notations carefully, listen carefully, and remember, you write these notations somewhere, and these properties, all these properties, write all these properties in some page, okay, so that you can easily access the result. So moving to our next proposition. What is the next proposition? Kernel T star T lambda conjugate is not equal to 0 if and only if kernel T lambda not equal to 0. What is the meaning of that? Kernel T star lambda. What is kernel T star lambda? And what is kernel T lambda? Kernel T lambda is not equal to 0 means kernel of T minus lambda is not equal to 0. That means T minus lambda is not 1 1. Now what is T lambda star? T lambda star. Here we are saying T lambda is not 1 1. Then what is T lambda star? T minus lambda I star, that's equal to T star minus lambda I star. But we know that lambda I star is lambda conjugate I, that is T star lambda conjugate. So T lambda star means T star lambda conjugate. So T star lambda, now kernel of T star lambda conjugate means kernel of T lambda star not equal to 0. So this result says that T lambda not 1 1, T lambda not 1 1 if and only if T lambda star is not 1 1. That is T lambda star is 1 to 1 if and only if T lambda is 1 to 1. This is the result, and there is no need to write this for exam. Now moving to proof of our proposition. The proposition says that T lambda not 1 1 implies T lambda not 1 1 implies T lambda star is not 1 1, and conversely. So for suppose this we are taking this part. That means kernel T lambda not equal to 0. So kernel T lambda not equal to 0 by proposition 5.2.5. What is kernel T lambda not equal to 0 implies delta lambda not equal to x. Okay. So delta lambda not equal to x. Now what is delta lambda? Here actually delta lambda not equal to capital X. Delta lambda not equal to capital X. So what is the next theorem? Delta lambda not equal to x implies kernel t star lambda not equal to 0. Delta lambda not equal to x implies kernel t star lambda conjugate not equal to 0 by proposition 5.2.8. Therefore, kernel t lambda not equal to 0 implies kernel t star lambda conjugate not equal to 0. Thus, we get one implication. Okay. So actually we are proving the converse part. Kernel t lambda not equal to 0 implies kernel t star lambda conjugate not equal to 0. Okay. Now we have to prove the converse part by proposition 5.2.7. Delta star lambda conjugate equal to x star implies kernel t star lambda equal to 0. So in the first part, we are assuming kernel t star lambda conjugate is not equal to 0. And kernel t lambda, what is kernel t lambda? Kernel t lambda by second proposition, kernel t lambda equal to delta star lambda conjugate perp. Also, kernel t lambda perp equal to delta star lambda conjugate. Okay. So assume the first property, kernel t star lambda conjugate is not equal to 0. That means kernel t star lambda conjugate not equal to 0 means kernel t star lambda conjugate is not equal to 0. Delta lambda kernel t star lambda conjugate not kernel t star lambda conjugate not equal to 0 implies delta star lambda conjugate is not equal to x star. Once again, here we have kernel t star lambda conjugate not equal to 0. This not equal to 0 implies delta kernel t star, the meaning of this one, delta lambda equal to x implies kernel t lambda equal to 0. Equivalently, kernel t lambda not equal to 0 implies delta lambda not equal to x. Therefore, kernel t star lambda conjugate not equal to 0 implies delta star lambda conjugate not equal to x star. That's what we have. Delta star lambda conjugate not equal to x star. Now, delta star lambda conjugate is kernel t lambda perp. Kernel t lambda perp not equal to x star. Now, what is kernel t lambda perp? Set of all f belongs to x star such that f of kernel t lambda equal to 0. By the definition of L perp, what is L perp? Set of all f belongs to x star such that f of L equal to 0. So this is not equal to x means there exists some linear functional f for which f of this not equal to 0. Therefore, the kernel t lambda perp not equal to x star implies there exists a f belongs to x star such that f of kernel t lambda not equal to 0. Now that means, what is the meaning of that? F of L not equal to 0 means there exists an x in L such that f of x not equal to 0. This implies there exists an x belongs to kernel t lambda such that f of x not equal to 0. Note that f is a linear functional. F of x not equal to 0 implies x must be not equal to 0 because f of 0 equal to 0. So f of x not equal to 0 implies clearly x not equal to 0. That means there exists a x not equal to 0 element in kernel t lambda. That means kernel t lambda not equal to 0. Thus we get kernel t star lambda conjugate not equal to 0 implies kernel t lambda not equal to 0. Thus we get kernel t star lambda conjugate equal to 0 if and only if t lambda not equal to 0. Clear? You have to remember this. And here, this is actually the result. T lambda is 1 to 1 if and only if T lambda star is 1 to 1. Right? That means A star is 1 to 1, A is 1 to 1. Operator A is 1 to 1 if and only if A star is 1 to 1. Okay. So now moving to next proposition, proposition 5.2.10. 5.2.7 may be inverted. That is, kernel T lambda equal to 0 implies delta lambda equal to x. What is our 5.2.7? This is delta lambda equal to x implies kernel T lambda equal to 0. And here 5.2.9 says that this statement, this can be inverted. That means kernel T lambda equal to 0 implies delta lambda equal to x. Now what is the meaning of that T lambda? Earlier it was T lambda is on to implies T lambda is 1 to 1. Here T lambda is kernel T lambda equal to 0 means T lambda is 1 to 1 implies delta lambda equal to x. That means image of T lambda equal to x. That means T lambda is on to. So here we are going to prove T lambda is 1 to 1 implies T lambda is on to. So what is from 5.2.7 and 5.2.10 we get T lambda is 1 to 1 if and only if T lambda is on to. We will check. Assume kernel T lambda equal to 0. Okay. So by previous this one kernel T lambda equal to 0 implies kernel T star lambda conjugate equal to 0. Here we have kernel T lambda not equal to 0 implies this one. So converse part also true. Okay. So kernel T lambda equal to 0 implies kernel T star lambda conjugate is equal to 0. So using 5.2.8 kernel, what is kernel T star? 5.2.8. Delta lambda equal to x implies kernel T star lambda no, not equal. That means converse part is, what is the converse part? Kernel T star, sorry, delta lambda not equal to x implies kernel T star lambda equal to 0. That means kernel T star lambda equal to 0 means delta lambda equal to x. So we are using that result. So kernel T star lambda equal to 0 implies delta lambda equal to x. So that's what we have to prove. Kernel T lambda equal to 0 implies delta lambda equal to x. So here we assume kernel T lambda equal to 0. By proposition 5.2.10 we get kernel T star lambda conjugate equal to 0. And by proposition 5.2.8 again we get delta lambda equal to x. Therefore T lambda is 1 to 1 if and only if T lambda is on to. Earlier T lambda is 1. Here we get delta lambda is 1 to 1 implies sorry, T lambda is 1 to 1 implies delta lambda is T lambda is on to. Earlier T lambda on to implies T lambda 1 1. Now combining both we get T lambda is 1 to 1 if and only T lambda is on to. Moving to next theorem. This is also very important. For any compact operator T from X to X in an infinite dimensional Banach space, we have sigma T equal to 0 union sigma P of T. What is the meaning of that? What is sigma T? Set of all spectrum point. Okay. Set of all spectrum point equal to 0 union set of all point spectrum. What is set of all spectrum values? An element lambda belongs to sigma T means lambda not belongs to rho of T. That means lambda not belongs to rho of T. That means T minus lambda I is not invertible. Okay. What is the meaning of that? T lambda t minus lambda I is equal to T lambda. T lambda is not invertible. That means T lambda is not one to one and on to. Now what is here? What we have sigma pt point spectrum. Point spectrum means set of all eigenvalues. Set of all eigenvalues. That means set of all lambda such that t minus lambda I there exists an x not equal to 0 such that t minus lambda I x equal to 0. Set of all eigenvalues. So this says that uh, sigma t is actually 0 union sigma pt. So what is sigma? Clearly we know that sigma pt means set of all I clearly is a subset of sigma t because sigma pt means there exists an x not equal to 0 such that t minus lambda I x is equal to 0. That means this is not one to one. Okay, therefore clearly this is not invertible. That means that is sigma t. What about 0? If you take 0, clearly 0 is also in. If you take 0, lambda 0, then clearly what we get 0 is also in spectral value. Already we have proved sigma t. 0 belongs to sigma t. Okay. So what we have to prove is if lambda not equal to 0 and lambda not belongs to sigma pt, we have to prove this is equal to union of these two. That means if you take any lambda and lambda not belongs to sigma pt, then that cannot be a in sigma t. That means that is not a spectrum point. That is we have to prove that is a regular point. Okay. So let lambda not equal to 0 and lambda not belongs to sigma pt. The lambda not belongs to sigma pt means lambda is not an eigenvalue. Okay. That means for every x not equal to 0, for every x not equal to 0, tx is not equal to lambda x. This implies t minus lambda I x is not equal to 0. Lambda is not an eigenvalue means for every x not equal to 0 we get t minus lambda I x not equal to 0. That means tx is not equal to lambda x. Okay. Sorry. For every x not equal to 0, tx not equal to lambda x. That means t minus lambda I x not equal to 0. That means t lambda x not equal to 0. Therefore, lambda is not an eigenvalue implies there exists an x not equal to 0. For every x not equal to 0, t lambda x not equal to 0. But we know that t lambda 0 equal to 0. Therefore, if you take any x not equal to 0, then t lambda x is not equal to 0. Therefore, kernel t lambda consists only one point, that is 0. Kernel t lambda equal to 0 implies delta lambda equal to x. That means t lambda is 1 to 1 and on to. That means t lambda is invertible as t is compact and bounded. T lambda is also bounded. Thus we get T lambda is invertible and T lambda is bounded. This implies lambda belongs to rho of T. This implies lambda not belongs to sigma T. Okay. Clearly 0 belongs to sigma T and sigma Pt is contained in sigma T. Thus we get sigma T equal to 0 union sigma Pt. Now moving to next, Fredome's first theorem. What is Fredome's first theorem? Fredome's first theorem is actually our 5.2.9. I think 2.9. This one. Okay. So Fredome's first theorem is actually our theorem 5.2.9, proposition 5.2.9, and this says that sigma pt minus set 0 is equal to sigma pt sigma p of t star conjugate minus set 0. Okay, What is sigma p t star? Set of all lambda such that lambda is an eigenvalue of set of all lambda such that lambda is an eigenvalue of t star. Now sigma pt star conjugate means lambda conjugate such that lambda belongs to sigma p t star. Okay, let lambda not equal to 0. If lambda belongs to sigma pt, what is the meaning of that? Sigma pt means lambda is an eigenvalue of t. That means lambda is an eigenvalue of t means kernel of t lambda is not equal to 0. Lambda is an eigenvalue means there exists an x not equal to 0 such that t minus lambda I x equal to 0. That means kernel of t lambda is not equal to 0. So lambda belongs to sigma pt if and only if kernel t lambda not equal to 0. So using our proposition 5.2.9 we get this implies kernel t star lambda conjugate not equal to 0. And that implies lambda is not a. This not equal to 0 means lambda is a lambda is an eigenvalue of t star. This implies lambda conjugate is an eigenvalue of t star. This implies lambda conjugate not belongs to sigma p t star. Therefore, lambda belongs to sigma pt if and only if lambda conjugate belongs to sigma p t star conjugate. Therefore, sigma pt minus set 0 equal to sigma pt star conjugate minus set 0. Okay. Now, Fredholm's second theorem. Second theorem says that let lambda not equal to 0 and y belongs to ax, then the equation tx minus lambda x equal to y, that is t minus lambda x equal to y, that is t lambda x equal to y, has a solution. This equation has a solution if and only if y is orthogonal to all the solutions of the homogeneous dual equation. That is, y is orthogonal to all the solutions of homogeneous dual equation. What is homogeneous dual equation means? Homogeneous dual equation is t star f minus lambda conjugate f equal to 0. Okay, this has a tx minus lambda y equal lambda x equal to y has a solution if y is orthogonal in all the solution of this equation. Now, what about the solution of this equation? This solution means set of all f such that t star minus lambda I f equal to 0. This is the solution set. And this is actually kernel t star lambda conjugate. So, y is orthogonal to kernel t star lambda conjugate. That means y belongs to kernel t star lambda conjugate lower upper. So RHS consists of all functional, that means we are considering lower per. So the theorem says that t lambda x equal to y has a solution if and only if y belongs to kernel t star lambda conjugate per. T lambda x equal to y has a solution if and only if y belongs to kernel t star lambda conjugate lower per. So consider this equation t star f minus lambda conjugate f equal to 0. This implies f belongs to t star lambda conjugate. Clear? Now let f1, f2, etc. fk be the maximal set of linearly independent solution of equation 1. Okay. So, but we know that lambda, what about lambda as Banach space, and we know that multiplicity of lambda is finite. So as lambda is finite and it is of finite multiplicity, the values, what about the values f1, f2, etc., fkr, this set is also finite because this is the solution set of t minus t star f minus lambda conjugate f. Okay. And the multiplicity of each lambda finite means this solution set is also finite. Okay. Note that tx minus lambda x equal to y implies t lambda x equal to y. This has a solution. Okay. If this is equal to this has a solution means we have to find some x such that t lambda x equal to y. These are equal if and only if f of t lambda x equal to f of y for every f belongs to x star. Okay. If this has a solution, then f of t lambda x equal to f of y for every okay. So you can write as implies. That is what is about f of tx. We have a star phi equal to phi of x. Okay. Therefore, f of t lambda you can write as t star lambda conjugate f of x. Actually, this is t lambda star phi, and t lambda star is t star lambda conjugate phi. Okay, here for phi we have f here. T star lambda conjugate f of x equal to f of y for every f belongs to x star. Note that f is a solution of t star lambda conjugate f. Okay, that means but we get t star lambda conjugate f equal to 0, then t star lambda conjugate f of x equal to 0, and each fi's are linearly independent solutions of this one. That means we get t star lambda conjugate fi of x equal to 0 for I equal to 1 etc. Okay, but t star lambda conjugate fi of x equal to, by definition, this is f of y, fi of y. Okay, so fi of y equal to 0 for I equal to 1 etc. Okay, that means y belongs to kernel fi. Okay, now let f belongs to kernel t star lambda conjugate, and fi's are maximal independent set. We can write f in terms of fi's, linear combination of fi. That means f you can write as f equal to I varies from 1 to k ai fi. Therefore f of y is this one, and as each fi of y equal to 0, therefore f of y equal to 0. Therefore, for every f belongs to kernel t star lambda conjugate, f of I equal to 0. Now, what is f lower perp set of all x belongs to x such that f of x equal to 0 for every f belongs to capital F. Therefore, for every f belongs to kernel t star lambda conjugate, if you take any y, we get f of y equal to 0. That means y belongs to kernel t star lambda conjugate lower perp. Thus we get t lambda x equal to y implies y belongs to kernel t star lambda conjugate perp. Okay. Now conversely assume that y belongs to kernel t star lambda conjugate perp. That means f of y equal to 0 for every f belongs to kernel t star lambda conjugate perp. That means, what is the meaning of that? T star lambda conjugate f of x equal to 0 because f belongs to kernel t star lambda perp. Okay, so t star lambda conjugate f of x equal to 0. That means f of t lambda equal to 0. F of t lambda x equal to 0 means f of t lambda of x equal to f of y, because f of y is also equal to 0. That means t lambda x equal to y. That means uh, t minus tx minus lambda x equal to 1. That means if y belongs to kernel t star lambda conjugate per, we get this equation has a solution. Okay. Now if t star f minus lambda conjugate f has only a 0 solution, okay, then t star lambda conjugate I f equal to 0 has only 0 solution. That means lambda conjugate is not an eigenvalue of t star. That means lambda is not an eigenvalue of t. That means t lambda is invertible. Therefore, t lambda x equal to y implies you can write x equal to t lambda inverse y. Okay, therefore if f equal to 0, that means this has only a 0 solution. F equal to 0, we get tx minus lambda x equal to y has a solution for any y belongs to x. That is Fredom's second theorem. And Fredom's third theorem is dimension of kernel t lambda is equal to dimension of t star lambda conjugate. But we have kernel